Okay, thanks. I'd like to begin by thanking the organizers for this opportunity to speak, and of course it's great to be here in Rio. So I'm going to talk about two inequalities, one joint work with Neil Bez and one joint work with Toru Ozawa. So I have to apologize because there's nothing nonlinear, but at least one of them has been useful in nonlinear theory. Okay, so first of all, we'll talk about the Strichartz estimate. So I'm going to talk about, the whole time, I'm going to talk about the wave equation. And so nothing about the Schrodinger equation will appear on the slides. And I'm sort of hoping I'll remember to cite the correct people. I said almost everything happened for the Schrodinger equation, and then it happened for the wave equation later. So everything has a Schrodinger precedent. So this is the Strichartz estimate, proven by Strichartz, so it's a space-time estimate in the sense that you integrate over the d spatial variables and also over time. And you bound that by the initial data. So this u naught, if I just write u naught with nothing else, that means u at time 0. So if this is time, that's what I mean by that. Okay, and of course, this is conserved for all time. So you can change this 0 to any time and it stays the same. Okay, so the maximizers for this were calculated by Foskey in 3 dimensions. He also did the Schrodinger equation in 1 and 2 dimensions. And more recently, Ramos proved the existence in the other dimensions. And so what we're going to talk about today is this inequality, which, so by the conservation of this for a fixed time or something similar to it, this is also conserved for all time, the energy. So in the nonlinear theory, there's such a thing with another LP term, which is the energy, and that's conserved for all time. And so it's possible, sometimes this has been used just as much, I believe, in the nonlinear theory as this one, because in the nonlinear equations, you've got something like this, which is conserved for all time, called the energy. What was I going to say? Oh yeah, so the fact that you have some conservation, you can have an L infinity in time estimate with some L2 in space, and you can interpolate with that and then do some Sobolev embedding and get that. All right, so this is often called Sobolev-Strichartz estimate. So the maximizers for this one were proven by Bullitt, using the profile decomposition of Barouri and Gerard. So Ramos also proved the profile decomposition in order to prove the existence of maximizers, as was done here. And this, and Finelli, Vega, and Visilia essentially proved maximizers for all Sobolev-Strichartz estimates of any type using a more direct argument without getting the profile decomposition first. Right, and so what I'm going to talk about is this. So with Neil Bez, we've calculated the maximizers for this inequality when d is equal to 5. All right, so this is the inequality. So what I like about it, is that is that it's a real, so this can be considered to be a real equation, of course, waves. And this is real. You know, so now we don't need the Fourier transform. The H1 norm, you need the Fourier transform to define it and so on. And it's in some sense complicated object. This is a very simple object. This is just derivatives in space. This is derivative in time. So you can think of this as smooth solutions, classical solutions. And this is a real inequality. And the proof, as we'll see, needs complex numbers and the Fourier transform and so on. Well, our proof does. And so the constant is sharp, and it's attained for these maximizers modulo the action of all these symmetries. So of course the wave equation, if you translate it from side to side, it stays the same. So your translations of this are also maximizers. And then you have some less obvious symmetries, some dilation, and then this one is, I haven't even defined it. I'll tell you what these things are later. So this is somehow factorizing the solution. So the solution to the wave equation is cosines and sines, plus sines, which can be factorized into exponentials, right? The cosine is equal to exponential plus exponential over. And so this is, so u is equal to u plus u minus in this exponential factorization. All right. So I just mentioned the other inequality now, just for comparison purposes. So it's the same equation, this time in more dimensions. And we're again integrating in space and time. But now we have some weight, which gives you decay at infinity, so it's somehow a local estimate, but on the other hand, it gives you some singular at the origin. And this is the sharp constant, and this is the same norm as before, this energy norm. So Morowitz proved an estimate of this form for the nonlinear Klein-Gordon equation first, and then a number of other people have proved for the nonlinear equation. So I don't know if anyone's considered for the linear equation, and I don't know if it will be of any use, probably not. So an equality is attained if and only if these are radial. So now we have a very large class of maximizers. So that was just to tell you the result. So I'm going to go back to this one now. I'm going to try and give some details of the proof of this one first, of the Strichartz estimate. So as I was saying before, you can factorize the wave equation into, this is the plus, U plus operator, one-sided operator. So this is in red to remind me to say, so even though this is a talk about sharp constants, even in a talk about sharp constants, the constants are not important. So from now on, I'm going to ignore these 2 pi's. So everything is true modulo factor of 2 pi d's. And so the wave equation estimate is a consequence of this one-sided estimate. I mean, it's not entirely trivial to get the wave equation estimate from this one-sided. That's an argument of Foskey again, but I won't present it. I mean, essentially it uses that 4, of course 4 is important here. 4 is 2 times 2, and that means we can use some Plancherel and orthogonality in order to recover, rather than recovering trivially via the triangle inequality, an estimate for u is less than or equal to one of these plus another one of these. We can use some orthogonality to keep the sharp constant. And now the maximizers are taking this form. And this estimate, this linear estimate for the one-sided operator, will follow from a bilinear estimate for the one-sided operator. So now we're in lots of dimensions, And so what can I say about this? So this weight, when d is equal to 2, this is singular. And so this is like a traditional, I don't know if traditional is the right word, but like the other bilinear estimates, which have been seen in the past, in that you need to keep the frequency supports separated, because otherwise the singularity makes this side infinite. So when d is equal to 2, this is a sort of normal bilinear estimate, in the sense that you need an extra condition in order for it to be true. When d is equal to 3, this estimate is due to Foskey, because then you recover, this disappears, and you have, so this integral factorizes completely. And you can, so by Cauchy-Schwarz, you can recover the three-dimensional Strichartz estimate with half a derivative. And so why can we do something when d is equal to 5? We can do something when d is equal to 5 because when d is equal to 5, this is equal to 1. So that's somehow more tractable. Right, so I'm just going to rewrite this again, but putting d equal to 5. Right, and so I've mucked around with it a little bit, but that's exactly what was on the previous slide. So, so now this weight, keep that weight in mind. So this weight is somehow important. So something similar to this was proven by Carneiro for the Schrödinger equation. And a crucial observation of his is that, so what can we do with this weight? Of course, you can bound this whole thing by you can kill that if you put another 2 in the front, right? Because this is, so when y is equal to minus eta, this is exactly equal to 2 times by these guys. So you incur an extra 2 in your constant. Of course, that's not sharp. But what you can do is this. So now we're just looking at this, just going to concentrate on this term here, and I just write this whole thing as big capital F and capital G. So if we look at that, so if we just write this dot product out, the dot product is equal to y1 times eta 1 plus y2 times eta 2. And so that's all I've done here. This step, I just write out this sum and pull the sum out here. So absolutely nothing happened there. And then you notice that this factorizes completely, right? So this is integral in y, and this is an integral in y, and this doesn't depend, neither of these bits depend on eta. So we can actually separate that out completely. And then, of course, this is equal to this one. So that's squared. So we see it's always positive. And not only is it always positive, obviously when f is radial, when you go through the origin, this changes sign. And so as you integrate, it cancels. So for radial functions, as well as others, that's 0. So if this is always positive, this part of the integral is always positive, then this part of the integral is always negative, right? Negative sign in front of it. So if this is always negative, I can throw it away. And I can bound this whole thing by exactly the same thing, ignoring that. And the equality is obtained when f is equal to g is radial. And these guys are radial. So, what else? So now I'm going to try and give an idea of the proof. So we want to calculate this. Right, so an obvious thing which springs to mind is by Plancherel's theorem, this is equal to the Fourier transform of this. But the Fourier transform in space and time. So I'll just quickly calculate the Fourier transform of this object, the Fourier transform in both variables, space and time, of this object. So this is this formula here is what, the Schrodinger, the one-sided wave operator is defined by this. So I've sort of put the two integrals together. And nothing happened here. This is just the wave modulation and the inverse Fourier transform. And I'm taking the Fourier transform of this. This is the inverse Fourier transform in space. And now I'm going to take the Fourier transform in time and space. So just write this out. So the Fourier transform, of course, is defined by this. You take another couple of integrals. And then you do Fubini, put the things inside. This tau comes in with this. And this x, this chi, comes in with the y plus n, eta. And of course, the Fourier transform of 1 is the delta function. Evaluated at this. And the Fourier transform of this, the Fourier transform of 1, the Fourier transform of 1 is the delta function evaluated at here. So initially, it's going to be convenient to consider the Fourier transform to be this, but also later so of course, the Fourier transform of two things multiplied together is the convolution of two Fourier transforms. So the Fourier transform, the space-time Fourier transform of one of these guys is this. And a similar thing, calculation. And so this is the convolution of these two guys. That's just a strange way of writing that convolved with that. Okay, so the proof. So we want the L2 norm of this pair of waves. And we've already seen that the Fourier transform is this. So we want the L2 norm of this, the square of the L2 norm of this. Now, Foskey's, key idea was to operate directly, instead of integrating this thing and then start playing with it, he just played with it immediately, right? So he did Cauchy, first of all, so this is different from what Foskey did. So we multiply and divide by this weight. In fact, Foskey also did this with these, he might have hidden it, but he would have done this. So of course we can multiply and divide by whatever we want first. And we put this weight. Of course you do these things and then you find out what weight you need, but we'll do it in the reverse order. So you multiply and divide, and then you do Cauchy-Schwarz with respect to this measure. So by Cauchy-Schwarz, that's a lot of symbols, but there's nothing happening. I've just done Cauchy-Schwarz with respect to this measure, and of course, this becomes squared, and then in the other bit, this becomes squared. So we get that. Now, what we'll prove in the next slide is that this is constant for a fixed. At the moment, we're going to take the L2 norm in chi and tau in the Fourier variables. But at the moment, these guys are, the chi and tau variables are fixed, and we've got integrals in these other variables. Now this integral is actually is constant. It's a constant function of tau and chi. I guess that's not surprising. Anyway, so I don't know. It's absolutely constant, right? It's absolutely constant. So now, if you do it without the weight first, it becomes a function of chi and tau, and that tells you what the weight needs to be. But anyway, so we've already done it. So there's an absolute constant. So in order to complete the argument, once we've proven that this is an absolute constant, you take the L2 norm of this guy. Now, the L2 norm squares this, and then you integrate in chi and tau. And of course, these deltas, there's always a tau equal to this yn, so you do Fubini, and you take the integral in tau, and the integral of the delta gives you 1, and then you take the integral in chi, and the integral of the delta gives you 1. So you end up with exactly what we want, this bilinear the left-hand side of the inequality that I told you before with this weight, as we saw before. So it remains to prove that this is an absolute constant. And we need to know exactly what that absolute constant is. So a key part, a crucial observation is, or not observation, crucial fact is this. But I'll start on the wrong side. So tau squared minus chi squared, because on these delta measures, on the support of these delta measures, tau is equal to mod y plus mod eta, and chi is equal to y plus n, eta. So I can replace tau by y plus eta. I can replace chi by y plus eta. And then if I multiply these guys out, the y squared cancels with the y squared from here, and the eta squared cancels from the eta squared from here, and I'm left with 2y eta from here minus 2y dot eta from here. So that's 2 times the weight. All right, and that's why the weight was chosen, because this pops out when we calculate the integral without the weight. Okay, so we want to calculate this. And as we've seen, on these delta measures, on the support of these delta measures, we can just pull this straight out because it's constant. All right, and then we're left with this, and so that integral, or that line, is equal to where mu is this measure that I told you about before, mu of tau and chi right? Well, you can recognize, I mean, we saw exactly this integral before, and it was the convolution of 2 of these guys. Now, why is that interesting? Because this you can calculate is equal to this. Right? That's just a simple calculation. And from this representation, it's easy to see that you can do the following change of variables. You can change chi to chi minus chi as long as you change t to t star equal to tau squared to the 1/2. Right? It's obvious from this representation, if you move chi to 0, then you can compensate for that by writing this instead of t, because you take the square of that and you get exactly the same thing as you had before. So this is called the Lorentz transformation, or can be interpreted as Lorentz transformation. And so the fact that this measure is Lorentz invariant means that this measure is Lorentz invariant, means that also the convolution of the 2 is Lorentz invariant, so this object is Lorentz invariant. So here I can subtract chi from chi as long as I change tau to tau squared minus chi squared all square root. So that's the next line. That's the only hard line. All right, so I've changed chi to 0, and I've compensated by writing t squared minus chi squared to the half. And then everything else is plain sailing. So, although it's lots of formulas, it's very easy. So this, you can just integrate the y, and this delta is fulfilled, and the integral of this delta is equal to 1, and y is forced when y is equal to eta. So I change, or eta is equal to y. So I change eta to y, and I get 2y here. Eta changes to y, I get y squared. And then by homogeneity, I can scale this to 1, paying with this factor. And of course this cancels, and that's why we chose it all like this. And then you can calculate what this is by polar coordinates. It's equal to this measure of the sphere or something. 2 times the measure of the sphere. Well, an eighth of the measure of the sphere. So that's a constant. You plug that in before. And so we didn't really. So the only place that is not an equality is the Cauchy-Schwarz inequality. So this is the only inequality, and you can fulfill that as long as this guy is equal to this guy on the support of the measures. So because you're multiplying this by this, the good idea is to take something along this line, something along so if you take f hat of y to be something like that, when you multiply it by g hat eta, then you get the multiple of those two things is e to the minus t, which is constant again on the measures. So that this is constant. This is constant on the measures. This is constant on the support of the measures. This is constant on the support of the measures. And then you just choose some powers of y's and eta to balance that up. All right, and that's why we had, in fact, the maximizers with that kind of thing. And we moved those things around in the first place because we knew that when we got to here, we'd be able to calculate it because it's Lorentz invariant. You need an extra bit of symmetries in order to be able to calculate these things. There's nothing more to it than that. You do what you can do.
2 more minutes.
2 more minutes. Wow. So, a brief sketch of this proof. So, of course, it comes from a one-sided thing again. I won't go into that. So, I'm just going to prove one-sided inequality. And how I do this is you write it in polar coordinates. And then, by Plancher's theorem, so that I first saw this in Vega's thesis, that you write this in polar coordinates, and then you take the time. If you integrate in L2 in time, then you can view this bit as just a Fourier transform and kill it. And then the step of interest is you multiply out this whole thing. Then so again, we want this integrated in space with this singular measure. So now we have to integrate this in space multiplied by this singular measure. So that's just all that is. And then you notice that if you do Fubini and you're integrating in space, this is just a Fourier transform of this singular thing. But you can calculate that Fourier transform, and it's all evaluated on the spheres. So you get that, and then you plug in the sharp Hardy-Littlewood Sobolev inequality due to Lieb, and you get that, and you're essentially done. And that generalizes to other HS's.